So we're on page 73 and we're going to have a look at the final two types of calculations that you could be asked to do with respect to the pH of acids or alkalis. And the first one of those is dilution. So dilutions and neutralizations. If an acid or an alkali is diluted or neutralised, at least partially, then the pH of the acid or alkali is going to change. So let's have a look first of all at dilutions, and you could be asked to do this for an acid or an alkali, and in particular with the acids you could be asked to do it for a strong acid or a weak acid. It's a little bit more complicated with a weak acid, but in general we follow this same three-step process. We calculate the concentration of the new solution, we determine the concentration of the hydrogen ions, and then we use our pH equation to determine the pH from the hydrogen ions. So let's have a look at an example. And this example involves a strong acid. So here we've got 50 centimetres cubed of a 1 molar hydrochloric acid solution, and we're diluting it with 200 centimetres cubed of water. And we're asked to calculate the pH of the new solution. So what we want to do, if you look back at step 1, we need to calculate the concentration of the new solution, and in order to do that we need to work out the number of moles in the original acid and divide by the new volume. So let's see first of all how many moles of hydrochloric acid we had in the old solution. So we're having a look at the old solution of hydrochloric acid, and we're working out the number of moles. So N equals CV, our concentration is 1, and our volume is 50 centimetres cubed. So you can do 50 divided by 1000 or 0.05. And that gives us 0.05 moles. If we bring that over, this is not like a ratio moles calculation, but we're just bringing that number of moles to our new solution of hydrochloric acid. So the new solution of hydrochloric acid is going to still contain 0.05 moles, because when you dilute an acid or an alkali, the number of moles doesn't change, but the volume changes, and that's what affects the concentration. So you looked at that back at GCSE, so you need to remember that principle that when you're diluting an acid, it's going to contain the same number of moles. If you think of it in terms of a volumetric flask, we could be doing this in a volumetric flask, a 251. And in it, we have our 50 centimetres cubed of 1 molar hydrochloric acid, and we know in that there's 0.05 moles. If I add 200 centimetres cubed of water to fill it up to the mark, I'm not getting rid of any of my hydrochloric acid, it's still in there, but it's just more dilute now because there's a larger volume, but the number of moles stays the same. So back to working out the concentration of my new solution of hydrochloric acid, I need to divide the number of moles, which I know is 0.05 moles, by the volume. But before I do that, I need to work out what the total volume is, because I'm going to be using the equation C equals N over V. So I need to work out what my new total volume is. Okay, so I had 50 centimetres cubed of hydrochloric acid, and I then added 200 centimetres cubed of water. So the total volume of my solution is now 250 centimetres cubed, which is 0.25 decimeters cubed. So now I'm ready to put that straight into my equation. So the number of moles is 0.05, the volume is 0.25, and so the concentration is 0.2 moles per decimeter cubed. So now I've got the concentration of my new solution of acid. Step number 2 is then determine the H+. In order for us to do that, we need to think about what type of acid hydrochloric acid is. And so we have a look at how it dissociates. So hydrochloric acid is a strong acid, and so it will fully dissociate into its ions. And it is also a monobasic acid, so it only produces 1 mole of hydrogen ions for 1 mole of the acid. So if I have a solution of 0.2 moles per decimeter cubed of my hydrochloric acid, that means in solution, because of my 1-to-1 ratio, the concentration of my hydrogen ions will be 0.2 moles per decimeter cubed. So it's very simple to work out the concentration of the hydrochloric acid, or of the hydrogen ions for a strong acid. Then finally, remember we've been asked to calculate the pH. So we very simply put that into the equation for pH. pH equals minus log H plus. So in this case, it's the negative log of 0.2, which is equal to 0.70. So again, for this type of question, you've been asked for pH. Think ultimately, I'm going to need to use this equation. This is the only equation we know to work out pH. So I'm going to need the concentration of my hydrogen ions, because that's the only piece of information that I need for that. And in order to get that concentration of hydrogen ions, I first have to calculate the concentration of my new solution, my new dilute solution of hydrochloric acid, and then work out the concentration of hydrogen ions based on what type of acid it is. Okay, so the next question is looking at how we determine the pH of an alkali after it has been diluted. So this question tells us that we have 0.5 molar sodium hydroxide, 25 centimetres cubed of it, and it's diluted until the total volume is 500 centimetres cubed. And I just want to say at this point to be careful about the language that is used when they're talking about the dilution, because in the last question we were told that the solution was diluted with a certain volume of water. And so for that we had to take the total volume was the original volume of the acid plus the volume of water that was added. But in this case it's different because they tell us it's diluted until the total volume was 500 centimetres cubed. So we don't have to calculate the new volume, it already tells us the volume. So essentially what they've done is diluted it by adding 475 centimetres cubed of water. But what they've probably done is put it in a volumetric flask that was 500 centimetres cubed and just filled it up until it was at the top. So just be really careful when you're working out your total volume. Look to see whether they've already told you it. If they've said they diluted it to 500 centimetres cubed, then that's your total volume. If they say diluted it with 500 centimetres cubed of water, that means you need to work out your total volume by adding it to the original volume of acid or alkali. So same process here, we want to work out the concentration of the new alkali. And we do that in the same way that we did previously. So in the original solution, you can write old or original solution of sodium hydroxide. We want to work out the number of moles that we had of the sodium hydroxide. So N equals CV, our concentration is 0.5, our volume, our original volume, is 25 centimetres cubed, which is 0.025 or 25 over 1,000, and that gives you a number of moles of 0.0125 moles. So that's how many moles of sodium hydroxide I have in my solution, and that doesn't change even though my concentration changed. So here's my sodium hydroxide in the new solution, and it has 0.0125 moles in it. I can now work out the concentration by dividing the number of moles by the volume, and just as we were saying earlier, the total volume is now 500 centimetres cubed. I don't need to work that out. So that's 0.0125 over 0.5, which is your 500 centimetres cubed or 0.5 decimeters cubed, and that gives us 0.025 moles per decimeter cubed. So that's the concentration of our new solution of sodium hydroxide. From that, I need to work out my concentration of my hydroxide ions. So again, sodium hydroxide is a strong base or strong alkali, so it will fully dissociate into its ions. And it's the hydroxide ions that is going to affect the pH. Okay, so you can see that 1 mole of sodium hydroxide dissociates to give 1 mole of hydroxide ions. So if I have a concentration of 0.025 moles per decimeter cubed of sodium hydroxide, that means it's going to dissociate to give me a concentration of 0.025 moles per decimeter cubed of hydroxide ions in solution. Now, if I think ahead to how I'm going to calculate pH, I know that my equation for pH is minus log H plus, but I don't yet have my concentration of hydrogen ions. I only have the concentration of hydroxide ions. So I need to do an additional step at this stage to work out the hydrogen ions. So the equation I know to do that, to convert from hydroxide ions to hydrogen ions, is Kw equals H plus, concentration of H plus, times the concentration of hydroxide ions. Kw is 1 times 10 to the minus 14. And that equals the concentration of your hydrogen ions times by the concentration of your hydroxide ions, which we calculated to be 0.025. Bringing that over to the other side, H plus is going to equal 1 times 10 to the minus 14 over 0.025. And that gives us a hydrogen ion concentration of 4 times 10 to the minus 13 moles per decimeter cubed. And finally, I can now put it into my equation for pH. pH equals minus log H plus, which equals minus log 4 times 10 to the minus 13, which is 12.4. So again, same 3-step process. Calculate the concentration of your new solution. Work out the concentration of your H plus ions. This time we had the additional step of using our Kw equation because we're working with a base. And then finally calculate your pH using your negative log of the hydrogen ions. Finally, we'll look at an example that includes a weak acid, and this is a little bit more complicated because when we are looking at our second step of calculating our hydrogen ions, we can't simply do that using the dissociation equation of our weak acid, because we know that our weak acid only partially dissociates. If this is a general equation for it, we've got an equilibrium arrow for the dissociation into the hydrogen ions, whereas in the first example we had hydrochloric acid which fully dissociated into hydrogen ions. So when we calculated the concentration of our hydrochloric acid, we could go straight and work out the concentration of our hydrogen ions. But in this case, once we have our concentration of our weak acid, it doesn't fully dissociate to give us hydrogen ions. So we need to use our equilibrium calculations to work out the concentration of hydrogen. But the first step is exactly the same. But just at this stage, can I point out that this, rather than being 1.8 times 10 to the 5, should be 1.8 times 10 to the minus 5, if you could change that in your notes. Okay, so in my original solution of acid, this is talking about ethanoic acid. So in the original solution of acid, I need to work out my number of moles. The first step is the same. So the number of moles is the concentration times the volume, which the original concentration is 0.1, and the volume is 25 centimetres cubed, which is 0.025. That gives me a concentration of 0.0025 moles, or gives me a number of moles of 0.0025. So that's how many moles of acid I have. That doesn't change in the new solution, just the volume changes. And so I need to work out the concentration of the new acid. Okay, so I have 0.0025 moles of the acid, but I need to work out my total volume in this case, because they tell me I have 25 centimetres cubed of acid and it's diluted with. When you see that word with a certain volume of water, then you need to add it to the original volume of acid to work out your new total volume. So it's diluted with 500 centimetres cubed of water, so our total volume is 25 centimetres cubed, plus our 150 centimetres cubed of water that we've added in. That gives us 175 centimetres cubed, which is 0.175 decimeters cubed. So calculating my new concentration, I use concentration equals N over volume, which is 0.0025 moles over 0.175 decimeters cubed, which gives me a concentration of 0.014287 moles per decimeter cubed. So that gives me the concentration of my new dilute solution of ethanoic acid. But I can't calculate the concentration of hydrogen ions just using my dissociation equation, because we know that ethanoic acid is a weak acid and so will only partially dissociate to give its ions of its ethanoate ion and its hydrogen ion. So we need to use an equilibrium calculation in this case. So we need to work out our initial concentration, we need to work out our reacting concentration and our equilibrium concentration. And again, because we're sticking with the same volume now, we can use our concentration values rather than number of moles. So originally we have 0.014287 moles per decimeter cubed of my ethanoic acid, and at the start none of it will have dissociated into its ions. Once it has dissociated, I'll form a certain concentration of my hydrogen ions, which is what I'm interested in. So it will produce a certain volume, a certain concentration of my hydrogen ions. So I represent that by plus X. The ratio within my reacting concentrations is 1 to 1, so that's going to be plus X of my ethanoate ions and minus X of my ethanoic acid concentration. So your equilibrium moles is just initial plus reacting. So that's going to be 0.014287 minus X for the concentration of my ethanoic acid at equilibrium, X for the concentration of my ethanoate ions, and X for my concentration of hydrogen ions. So in order to work out the concentration of my hydrogen ions, I need to use an expression for Ka. So first of all, let's write it. So Ka is the concentration of my products over reactants. So that's the concentration of my ethanoate ions times by the concentration of my hydrogen ions over the concentration of my ethanoic acid. Back in the question, we were told that Ka is 1.8 times 10 to the minus 5. That's the value that I got you to change. And that's going to equal the concentration of my ethanoate ions, which is X, times by the concentration of my hydrogen ions over the concentration of my ethanoic acid, which is 0.014287 minus X. But as we saw before, because the value of X is so small, we can assume that this value here is roughly equal to 0.014287. Because so little of the acid is going to dissociate, we can assume that it's equal to the original concentration of ethanoic acid. We know that's not totally accurate, but it makes this calculation a lot simpler. So since X is so small, we can assume that 1.8 times 10 to the minus 5, which is our Ka value, is equal to X squared over 0.014287, our original concentration of the acid. Okay, bringing this value to the other side and multiplying it on the other side, we find that x squared is equal to 1.8 times 10 to the minus 5 times that number, which is 2.5714 times 10 to the minus 7. So to work out x, I need to take the square root of 2.5714 times 10 to the minus 7, which is 5.0709 times 10 to the minus 4. Okay, so don't lose sight of what we're trying to do. We're trying to work out the pH of the new dilute acid, and in order to do that, I need to use my pH equation of minus log H plus. So if I look back to my equilibrium calculation, the concentration of H plus at equilibrium is equal to X. I have just calculated that X is equal to 5.07 times 10 to the minus 4. So the concentration of my hydrogen ions is equal to X, which is 5.0709 times 10 to the minus 4 moles per decimeter cubed. So now I'm at my final stage of putting it into my equation for pH. So pH equals minus log concentration of my hydrogen ions, which is minus log 5.0709 times 10 to the minus 4, which is equal to 3.3. So again, we've followed the same three-step process, calculating the concentration of our new solution of acid, then working out the concentration of hydrogen ions, which was a little bit more complicated because we had to use our equilibrium calculation, and then putting that into our equation for pH to calculate the pH of the solution. What you should do now is try the questions on page 78, just questions 1 and 2, and they will help you put into practice these dilution calculations.